So let's jump right in. It looks like we're starting with functions, so we might as well talk about the definition. Usually when you're talking about functions, the easiest way to tell if something is a function is to just graph it and then apply the vertical line test. So if you can draw a vertical line that hits the graph in two or more places, it's not a function. Everything else is a function. So that's kind of the easiest way. So you could do that with these ordered pairs, and you could tell it's a function. The other way is just using the definition. So we might as well write down the definition and try and do it from first principles. So a function is a rule which assigns to each input only one output. So you can think of a function as being like a machine. And notice it's assigning each input to only one output, not one and only one output. So that's two different things. So basically the crux of this is you cannot see the same input. And when I say input, am I meaning X value or Y value? X value, right? X values are inputs, Y values are outputs. So you can't see the same input, X value, appear with two or more different outputs, which, as I said, we're thinking of as Y values. So it is okay to see two different inputs have the same output, right? So you could have 2, 1 and 3, 1, and that would be okay because you have two different inputs, but each of them only has the one output. But what you cannot have is like 1, 3 and 1, 5, because then you would have the same input, but they would have two different Y values associated to them. Okay, and you could think graphically they would be on the same vertical line. This one, we're okay because everybody has a different output. So 2 goes to 2, 4 goes to 6, 9 goes to 9. All of them are different. So that is a function. Pretty straightforward. The domain. So we can list these things. The domain. I think we already... Did we talk about this already or no? Maybe. I might have mentioned it. This is just the set of all X values. And similarly, the range, or analogously, is the set of all Y values, the set of all your outputs. So if you're looking at the notes so that it's not absent of context, let's just say given S is equal to this thing we have here, 2, 2, 4, 6, and 9, 9, we would have the domain. We just list the X values. So the first coordinates, 2, 4, 9, and the range would be the second coordinates, 2, 6, 9. So that's all we need to list. So 2, 4, 9. And it asks for the range, so 2, 6, 9. Okay, so is this one a function? Let's do the same test. So we have 4 appearing twice as an input, and it's going to two different places. It's going to 2, and it's also going to the number 6. Not allowed, right? Every input can only go to one place, right? So that number 4 is mapped to two different places. So this would be a no. Does that make sense? So sometimes we think of it this way. You can think of it as a mapping type of system. You could have your inputs and you could have your outputs, and the ordered pair appears if they are linked. So we only have two inputs, 4 and 6, and then our outputs are 2 and 6. And what happens, well, we see 4 is going here, it's also going here, and we see 6 doing the same thing, going to 2 and also going to 6. So those represent our 4 ordered pairs. This function idea shows up a lot of places. I was always taught of functions like a machine. I've used this analogy before. So, okay, you could think of like a vending machine as an actual literal function in real life. So all of the buttons you press are like the commands, right? So the thing is, that's behaving like a function, right? Because if you imagine just a soft drink machine, you press the Coke button, you expect to get a Coke out, right? If you press the Sprite button, you would expect to get a Sprite. So each button is only giving you one thing, and it's the thing that's shown in the picture, right? And you could have lots of different inputs all giving you the same product, but you're not mad about that, right? If you had 10 buttons that all said Coke, you've seen that machine where everything's Coke in it. That doesn't upset you because you know what you're getting. You just have lots of different buttons, so it has a larger inventory of a specific product. But you would be upset if you kept hitting the same button and it gave you different things every time. That would not be a function, right? If you kept hitting the Sprite button and one time you get a Sprite, the next time you get an orange juice, the third time you get a beer, it would be not very consistent. So that's why we think of these things as a function. So for this one, not a function. All right, so we checked that one. So the domain is just, you can still talk about the domain and the range. That's not a problem. It's just the set of the input values, and the range is the set of the output values, which is 2 and 6. Determine whether the following equation defines y as a function of x. So a lot of times I like to just graph these and then go from there. So I wonder, so this is not so hard to graph by hand because it is just a line. So if we have x plus y equals 29, did we do graphs of lines yet or no? Did we do graphing? Well, I mean, you have input-output lists, so we can practice it, I mean, regardless. So you could subtract x on both sides here. I know we did a lot with factoring and other stuff. I don't think we did much from the functional perspective, but basically, this is a line. This graph is a line with y-intercept equal to 29 and slope equal to -1. So the graph is going to be something like this, right? It's going to be going down. It's going to hit 29 up here somewhere. Wow, that's a bad graph. Should be hitting way higher. So it should be hitting somewhere up here, like at 29. It should have a slope of -1, which is essentially like 45 degrees. So the graph is something like this. Let me see. If we go to go to Desmos here. This is a good graphing program. So it's just desmos.com. I use it now. I basically never even take out a graphing calculator. I just go here. You can just type in the equation x plus y equals 29, and you'll see the graph. You might have to zoom out here because 29 is pretty high, but there you go. You see the line, and it's just that line going downward. So you can apply the vertical line test, right? The vertical line, if you draw any vertical line, it's going to hit that line exactly one time, no matter where you draw it. So that is a function. So for that reason, we would say, yes, this is a function. So this one and this one. So let's just reiterate what the vertical line test is. So this is a function. So we have the vertical line test. So if a vertical line intersects, let's say if any vertical line, because that makes it even more clear, intersects a graph 2 or more times, that graph is not the graph of a function. So all other graphs are functions. So the vertical line test really tells you what it means to not be a function, but if you know everything that's not a function, the complement, those things all have to be functions. So that means if you're trying to draw a vertical line, what is okay in terms of being a function means it either doesn't hit anything or it hits the graph exactly one time. And with any line that's not a vertical line, it's only going to hit it once. So this is a function. So for most things where you see equations, you can just go to something like Desmos, graph it, and say, okay, I know that it's a function. Or I know that it's not a function. The vertical line test is pretty easy to apply. Okay, x squared plus y squared equals 16. Anybody from their old pre-algebra days remember what this is a graph of? Anybody? It's a fairly common shape. Yep, circle. So it is a circle. We can check that. So this one was x squared plus y squared equals 16. So we get a circle. Remember, essentially x squared plus y squared is always going to be a circle centered around the origin, and you can tell how big it is. The number that it's set equal to is the radius squared. So notice this has a radius of 4. 4 squared is 16. So the circle, although it's a fairly common shape from geometry, does not represent a function for us, right? Almost every vertical line is going to intersect the graph 2 places here. So this is a no. And then this one is to evaluate the function. So evaluating functions with function notation just means whatever you're plugging in, you plug in exactly as is wherever x appears, but you need to include parentheses around it. A lot of times that's going to be tricky when you have more than one term or you have a negative. So let's have a look here. So number 5, our function f of x is x squared minus 2x plus 2. So A, we want to evaluate f of negative 9. So that means just replace all those x's by negative 9 in parentheses. And it does matter that you have it in parentheses. Negative 9 in parentheses squared is positive 81, but if you just type in negative 9 squared with no parentheses, that's negative 81. So it's very crucial that you use those parentheses. If you're in doubt, put parentheses around it, and it will come out correctly. So we get 81 plus 18 plus 2, so that comes out to 101. And then we have x plus 2. Again, this has more than one term. So everywhere we see an x in the original formula, now it's going to become an x plus 2. And you need parentheses around it for the same reason. So f of x plus 2, excuse me. We get x plus 2 quantity squared minus 2 times x plus 2 plus 2. So remember, x plus 2 quantity squared, you have to FOIL it? Yes. Oh, really? Oh, sorry. Somehow it, what's going on? Froze. Let me try to reconnect to, what's it called again? So stop sharing, and then I'll share again. Good? Okay. Sorry about that. All right. So squaring it, we have to do x plus 2 times x plus 2, which comes out as x squared plus 4x plus 4. And then distribute the negative 2. So we multiply the negative 2 through, so we get negative 2x minus 4 and then plus 2. So the plus 4 and the minus 4 go away, and we're left with x squared plus 2x plus 2, because the 4x minus the 2x is just 2x. And then the last one, minus x, same sort of drill. We have f of minus x, and we get minus x quantity squared, minus 2 times minus x plus 2, which comes out to x squared plus 2x plus 2. So that's what we want to enter. Oops, get out of the old exponent. Okay, so graphing, some of these things we have some kind of regular shapes to them. Let me just make a comment about vertical and horizontal shifts, because that way if you know the basic graph of your function, it's easy to take these known graphs and just kind of move them around. So the two most important ones are horizontal and vertical shifts. So for number 6, we'll first talk about vertical shifts. So let's just start for all of these. Suppose y equals f of x as a function. So there's 2 vertical shifts. If you do y equals f of x and then say plus some number k on the outside, what this does is this shifts f of x up k units. Okay, so that's exactly what we're seeing in this example. If you have the absolute value of x and you know what that looks like, we know that the second graph g of x is going to just be that first graph shifted up 9 units. So everything just moves up 9. So we'll get to that when we're done. If we have f of x minus k, this is going to shift it down k units. So the horizontal shifts might be backwards from what you expect. And I'll try and explain that. So horizontal shifts happen when you compose it, when you do that plus or minus k inside the parentheses. Does that make sense? So if we have y equals, let's say, f of x plus k, like this. So it's being composed with a function plugged into the parentheses. Do you think that's going to shift it to the left or to the right? Yeah, so you would think to the right because we always think of positive as being to the right. But here's the issue. It's actually going to shift it left k units. And let me try and explain why. If you think of your starting position as f of 0, right? If you just have a normal function f of x and you want to find the y-intercept, right? You plug in 0 for x. That's how you get the y-intercept. Now, if you look at f of x plus k, what number would you have to plug in for x to make the inside there 0? You would have to make x negative k, right? Negative k plus k comes out to 0. And where is negative k on the graph? That's to the left. So because you have to plug in something negative to make that input, to get that same input of 0, it actually goes to the left. It's a little bit backwards of what we think, but it's kind of more concrete if you think about the actual numbers. So this shifts f of x left k units. Which will leave f of x minus k to go right k units. So this shifts f of x right k units. So if we have our example here, so this example we just want to graph y equals the absolute value of x and y equals the absolute value of x plus 9, as we see here. The first graph, we know the absolute value just does this, right? It looks like a V. Right? If you have 1, you get positive 1. 2, you get positive 2. 3, you get positive 3. And then as you go to negative, you get the same value, but it's going to be the positive y value. So if you plug in x equals negative 3, you get positive 3. So it just looks like that V. So this is y equals the absolute value of x. And then if you're going to do this y equals x plus 9, absolute value of x plus 9, you're going to start up here at 9, and then you're going to get that same exact shape. So this is y equals absolute value of x plus 9, like that. So let's see how we do this. So we click to enlarge the graph. Okay, it actually gives you the shape, right? So the shape we want here is this V. So I just click here and here. So that's the first graph. Then I guess I save that. And then click it again. Then I click the V. Now I just want to go up to 9. And I get the same shape again. So once I save that, those look like the two graphs I want. All set. Okay, shifted 9 units up. Okay, vertical line test, pretty easy. We've already talked about that. Vertical line will hit the box 2 times. The y-axis, in fact, is the vertical line that does such a task. So y is not a function of x. G of 6. So again, this is just plugging in but looking at the graph, right? So if we're trying to find g of 6, that means we just come over here to 6. That's the input. And we want to find the y value where the graph appears. So it's this dot right here. So this dot has a y value of 7. So when you plug something in and ask you what the result is, you're looking for a y value. So the answer here should be 7. Negative 7. It's below the x-axis. Negative 7. So this one's the opposite, right? It's saying for what x value does this graph have a y value of 2? So we're looking at this horizontal line that goes across at 2. Does that touch our graph? Yes, right at this kind of point at the far left. What x value is that above? That is above the x value at negative 5. So negative 5 is our answer there. So it's always important to try to understand, are they asking for us an x or are they asking for a y? And then you can kind of adjust accordingly. So negative 5 is the x value. Okay. So first one, they're asking for f of negative 2 and they're asking for the domain. They list all the questions first and then they go through one by one. So what is the domain? Well, these arrows indicate that it keeps continuing and it's going forever and ever to the left and to the right and forever and ever down. The only place it isn't going forever and ever is upward. Okay, so the graph peaks at a y value of 4 and doesn't go beyond that. So since it goes, the domain is how far left are we going and how far right are we going, right? Because that's the span of the x values. Domain is talking about x values, so how far to the left, how far to the right. Well, we said it's going forever to the left and forever to the right. So that means the domain here is going to be all real numbers. So since it doesn't stop, we're going to go from negative infinity to infinity. Remember, that's our interval notation. So here we would just do negative, comma, negative, what's the inf, comma, so negative infinity to infinity. The infinities always get the rounded ones. Okay, then we want to look at the range. Well, the range is going to be how far up and how far down. We know it's going down forever, so the smallest number is going to go all the way to the negative infinity, right? So we're still starting at negative infinity for the range. And then we want to know how far upward we go. So we go all the way up, and we stop, and it hits exactly 4. So it goes all the way up to 4. Do we include 4? It looks like it's touching 4, right? If it's touching 4, it's not a boundary. It actually gets there and stops. It's the very last point it reaches. So we put that square box around the 4, if you remember that. That is indicating that we actually include that value. X-intercepts, those are just the 2 places for this graph where it hits the x-axis. So it's hitting the x-axis first at -3, and then also at 1. So this is just going to be -3, 1. So those 2 spots. And then the y-intercept, it's hitting the y-axis only at 3. So the y-intercept is 3. And then f of -2, again, we look at the x value corresponding to -2. So find -2 on the x-axis, and then go up or down until you hit the graph. I hit the graph, and then you want to look what is the y value that corresponds to that point. Well, that's -2 for x, and the y value is +3. So f of -2 is equal to 3. And then f of 2, same deal. We find 2 on the x-axis. In this case, we're going to have to go down till we hit the graph. It looks like it's right on the end of that arrow. So I would say that's the y value -5, right on the end of that point of that arrow. So -5 is what I'm going to put for the y value. Okay. Any questions there? The graph ones are kind of tricky, but a lot of them, if you're getting stuck, usually you're just getting mixed up into, should I be thinking about the x value or should I be thinking about the y value? So always kind of ask yourself simply, is this giving me an x value and I'm trying to find a y value, or is it giving me the y value and I'm trying to find the x value? A lot of times that can be the source of some conceptual difficulty. Okay, so we have a pretty similar thing here. So the first question is about the domain. So how far left and how far right? Well, we're left to this point. It's an open circle, so we don't include it, right? So this is going to be a -3 with a rounded grouping symbol. Then how far to the right? Goes all the way to x equals 0. So -3 to 0, round here, square here. So -3 to 0. And then the range, we're going from the bottom to the top. So the bottom is -1, which we're including. The top, the y value, it looks like is 8. So -1 to 8, do not include 8. That's just a boundary point. Any questions there? Okay. X-intercept, it hits the x-axis. I think it's -1 right there. And this graph's a little hard to see. Yeah, just at -1, so it hits the x-axis. While we're at it, let's note that it hits the y-axis at -1 as well. So those are going to be the 2 intercepts. -1 for both. Different points, but coincidentally the same value. Find the value of the function. What do we get when we plug in -2? So when we plug in -2, we get a y value of +3. Does everyone see that? Okay, increasing and decreasing. Pretty simple. Let's just write down. So a function is increasing if it goes upward from left to right. And we say a function is decreasing if it goes downward from left to right. So that is one of those things that for us is very easy when it comes to answering questions if we have a nice picture, if we have a good look at a graph. One of the things that you actually do if you say move to calculus is you learn about a concept called the derivative, and the derivative is something that allows you to find, one of the things it can do is it allows you to find places where the function increases or decreases without ever having to look at a graph. So you can just give me a formula, I can use the derivative, and then I can tell you exactly where the picture would increase or decrease without ever drawing it. So that's kind of one of the cool things that the derivative lets you do. In this case, it's pretty straightforward when we talk about increasing or decreasing. The graph is decreasing. Again, it's going everywhere from the left and the right. It's going to negative infinity and positive infinity. So it's going to be decreasing from negative infinity up to 0. Again, we're paying attention to the x values when we're describing increasing and decreasing. And then it increases from 0 all the way to the right to regular infinity. Does that make sense? So basically the left half of the graph is decreasing and the right half of the graph is increasing from the picture that we see. So they ask us kind of opposites, so we say it's increasing from 0 to infinity. And one comment I will make is you might say, well, should I use a square box or an open symbol? Well, for increasing and decreasing, we would consider flat. Do you think we would call that neither or both? So as a flat line, is it increasing or decreasing? So we actually say both. So, I mean, it's how would you know, until somebody tells you. Somebody just had to come up with it, right? Both of them make sense. You could say either or you could say neither. It's just they have a special term to talk about when it's explicitly not flat. So if you ever hear monotone, that means it's really only going up. It doesn't ever have any flat points. So if we say garden variety increasing or decreasing, they include that. But so you would say, okay, well, I would include 0. But the only reason I know not to include it is in the directions right here, it says open intervals. So when they say open intervals, they just mean always use the round symbols. Okay, continue. Decreasing, that was negative infinity to 0. And then see, where is it constant? So constant would mean flat. I guess we're just going to say nowhere. Because it's only flat maybe at that one moment. That's not enough time. It would have to actually have some width to it, which it does not. So we'd say there's no interval where it's constant. Okay, on to 13. So increasing. Increasing means it's going up. So there's kind of 4 segments to this graph if we're looking at it, right? We have the part until we get to x equals 0. So we're increasing until we get to 0. Then we're decreasing until we get to x equals 1. Then we're increasing until we get to x equals 2. And then we're decreasing thereafter after. So there are 2 parts where this graph is increasing and 2 parts where the graph is decreasing. And the increasing and decreasing parts are both disconnected. So remember, when you have 2 disjoint sections that you want to talk about as being part of the same solution set, you need to use that U to put them together, to kind of glue them together when you're talking about your intervals. So when they talk about increasing, we're going to say negative infinity to 0, and then 1 to 2. and then we put the u to glue those together. And then decreasing is going to be from 0 to 1, and then from 2 to infinity. And then we glue those together. So everyone see that on the graph okay? So it's really more practice with interval notation because the graph itself is not anything special. And again, no intervals where it's constant. If it were constant, you'd have to see something like flat, like maybe a shape that kind of looks like, like part of a trapezoid, let's say, the top part of a trapezoid. Okay, so first they ask for increasing. So as we said, that's going to be negative infinity to 0. And then we glue that together with that u. So let's find that u symbol. There it is. With the union. And again, 1 to 2 was the other interval. Again, it says open, so we're just always using those rounded grouping symbols whenever it says open like that. Ooh. Does it say... Use a comma to separate the answers. Yeah. So if they said write an interval that specifies where it's increasing, you would use the union. So for the actual interval that specifies increasing, this is how you would write it. It's just because the instructions say to use a comma here. That's the only reason. If they said just write the interval, you would write it like this. Knowing interval notation and writing this is actually a little bit strange. I would never write a question like that. Or I would never write the instructions for the answer like that, I should say. But anyhow, we want to go here from 0 to 1, and then from 2 to infinity. All right. Never constant. All right. Fair enough. So continuing with properties of graphs, let's see. Okay. Without graphing, determine whether the graph has an equation that is symmetric with respect to the x-axis, the y-axis, the origin, or none of these. So a couple of ways you could do this. One, you could go to Desmos and just graph it. But there are two special kinds of functions that you can talk about, even functions and odd functions, and they both have symmetries associated to the graphs. So it's a good time to bring those up. So 15. So given a function y equals f of x, so we say f of x is an even function provided it satisfies the following thing: f of minus x is equal to f of x. So that means if you go the same distance to the left of the y-axis and to the right of the y-axis, you will have the same y value, right? Because when you plug something into f, you get a y value. So this is saying if I plug in, say, -3 and +3, I would get the same value coming out there. So you would have the same values associated to them, to the left and to the right. And it would be an odd function. So, well, let's also specify even functions have y-axis symmetry. And then we say f of x is an odd function provided. So you still plug -x into the function, but you don't get f of x out. With an odd function, you get negative f of x. So you kind of get the same y value but with an opposite sign. So these functions have what is known as origin symmetry. So odd functions have origin symmetry. And where do they get their names? E.g., y equals f of x. Sorry, let's not use y equals. Let's just say f of x equals. F of x equals, let's say x to the nth power is a. This is the group of examples that kind of gave it its name, right? So this is an even function if n is an even number, and b an odd function if n is an odd number. Right? And that makes sense. If you just think about x squared, if you do 3 squared or negative 3 squared, you get 9, right? If you do negative 8 squared or 8 squared, you get 64. Let's say you did the third power, though, an odd number. If you do 2 to the third power, you get 8. But if you do negative 2 to the third power, you get negative 8. Okay, so if we go back to Desmos, we can see kind of what even and odd look like. So let's say we do y equals x squared. Notice it looks the same to the left and to the right of the y-axis. That's what the y-axis symmetry means. And these aren't all of them. This is just a big set of examples, right? You can have something more complicated. This is just an algebra class, but from trig, if you've ever seen that, the cosine of x, that's an even function, right? It's exactly symmetrical to the left and to the right. Odd functions, that has origin symmetry. How would you describe origin symmetry pictorially? I mean, we know f of negative x equals negative f of x. I kind of think of it as two flips. So if you take the top right half, or top right quadrant, let's say, and you flip it down and then over, you get the same picture. So if you flip the part in the top right corner twice, you should get the same thing. And even something like, say, the sine of x, again, you don't need to know anything about trig, you can just look at the picture. If you take this part and flip it down and then over, it lies right on top. So origin symmetry I kind of think about as flipping twice and getting the same picture. So this one, x squared plus 14, we know it looks just like x squared, which has y-axis symmetry, and the plus 14 just moves it up, so that doesn't change the symmetry at all. So this has y-axis symmetry. Okay, piecewise functions are not so bad. It's really just saying you have a bunch of different formulas, and you only apply certain parts of the formulas based on where the x value is. Okay, so this function right here says, if you have a negative number, x less than 0, we're going to use that top formula, 2x plus 3. If we have an x value that's 0 or positive, we use the bottom formula, 4x plus 5. Okay, so when you get your x value, you have to figure out which formula you're using before you know how to plug it in. That's all a piecewise function does. So for the first one, negative 2 is less than 0. So we're going to use the top formula, 2x plus 3. And we don't worry about anything else. So let me just write this here so we can be a little more explicit. So f of x. And you can have more than 2 pieces. You can have 10 pieces if you want. A common example of a place where you would see like a piecewise function. Let's say you went to the post office to ship something. They might have different prices based on like weights, right? From like 0 to 1 pound, a package costs $4.50 to ship. From 1 pound to 3 pounds, it costs $6.50. From, so you have kind of piecewise categories that the shipping classes get into. Or sometimes they even do it with like sizes of boxes now, right? So based on the volume, it costs this much. Based on the volume, and it kind of jumps up. You reach different classes. It's not incremental. Or it's not continuously incremental, shall we say. 2x plus 3 if x is less than 0, and 4x plus 5 if x is greater than or equal to 0. So A, we have f of negative 2. So we're using the top formula, 2x plus 3. So 2 times negative 2 plus 3. This comes out to minus 1. Zero, we should be using the bottom formula. So f of 0, we get 4 times 0 plus 5. So that comes out to 5. Notice if you use the top formula, you get something completely different, right? You would get 3. So you would get the wrong answer. And then the last part, C, f of 4. We're using the bottom part still. It's a positive number, 4 times 4 plus 5. That comes out to 21. Okay, so this should be the last one for tonight. Another piecewise function. So graph the function. Well, it's two pieces. The piece to the left of 0, 0 and the negative numbers, should be the line with slope 3, right? So a line with positive slope. And then once you're greater than 0, you're just a flat line at height 5, right? So the flat part should be on the right half of the graph. So because C and D both have a line with positive slope and negative slope, you can rule out C and D immediately. So we know it's between A and B. Well, on the right half on A, it has a y value of 5. On B, it has a y value of negative 5. So just from process elimination, we know that the graph has to be A. Oh, I hit. I don't want to continue. I wanted to check. Okay. The range. So, see, this one, they have the other instructions, right? It does not say use commas. It says interval notation, set notation, and the union operator. So it is specific. Anytime you would just use intervals, typically you would use a union operator. This one's a little funny, though. Let's take a look at the graph in a little bit bigger manner. So remember, range is just specifying bottom to top, right? We're just thinking about all the places the graph lives as we move up and down. Now, we know it's going down forever. So we're starting at negative infinity at the bottom, and then we go up to 0, and we include 0. So that's one piece. But then we jump up and we have this flat piece that's at 5. Well, that's the only other number. It's not an interval of values. It's just that one single y value. So we've got all the y values from negative infinity to 0, and then one additional y value. So remember, when you're specifying a list of y values, that goes inside squiggly brackets, right? When you list a set, like when we were listing domains, 2, 4, 6, they were inside squiggly brackets. So for this one, we should be going from negative infinity to 0 with a square bracket because we include 0, and then we glue it together with that union operator, and then we put 5 in squiggly brackets. So that's a little bit of a complicated interval notation to write, but I think we can do it. So negative infinity to 0, we include the 0. Then we use that union operator, and then we want to do squiggly brackets with a 5. Or braces, I guess they're called. There's a lot of names for grouping symbols. Okay, that's it, and this is a good place to stop because next time it moves on to difference quotients, and that's going to require some tricky algebra. So we'll save that for next Wednesday. So we'll end the homework portion of today here. Let me just stop the recording.